It is often said that a proton contains 2 up quarks and 1 down quark. And that a neutron contains 2 down quarks and 1 up quark. But this is not entirely true. There are 6 different flavors of quarks, which we have decided to call up, down, charm, strange, top, and bottom. If we define the electric charge of a proton as +1, then 3 of the quarks each have an electric charge of +2/3, and the other 3 quarks each have an electric charge of -1/3. Each quark has an associated antimatter equivalent, called an antiquark, containing the same mass but the opposite electric charge. The electric charge is responsible for the electromagnetic force. On the other hand, the strong nuclear force is due to a new phenomena, which has no analogy in classical physics. We call this new phenomena the color charge, even though it has no relationship to visible color in classical physics. The color charge of each quark can take 3 possible values. Let us invent labels for these 3 values and call them green, red, and blue. Green, red, and blue. The color charge of an antiquark can also take 3 possible values, which we will call anti-blue, anti-red, and anti-green. Anti-blue, anti-red, and anti-green. Besides quarks and antiquarks, the only other type of particles that contain this so-called color charge are particles called gluons. Each gluon possesses 2 color charges, 1 color and 1 anticolor of a different type, such as red and anti-green. Gluons do not possess any electric charge. We now know that electric and magnetic fields do not actually exist, and that the electromagnetic force is really the result of the fact that particles with an electric charge exchange photons with one another. Similarly, the strong nuclear force is the result of the fact that particles with a color charge exchange gluons with one another. It is this exchange of gluons that holds the quarks together inside protons and neutrons. When a quark emits or absorbs a gluon, its flavor does not change, meaning that an up quark stays an up quark and a down quark stays a down quark. But the color of the quark changes. A color is cancelled out by its associated anticolor, and the total amount of color charge is always conserved, just as the total amount of electric charge is always conserved. All composite particles, such as protons and neutrons, are what we call color neutral. This means that if we count the colors of all the quarks and gluons inside, we will always find the amounts of red, green, and blue to be exactly equal to one another. Although this is not shown in the animations, each system is in a quantum superposition of different possible states, and each quark and each gluon is in a quantum superposition of different possible colors. A gluon can split up into a quark and its associated antiquark, provided that the total color charge is conserved. These events can also happen in reverse, with a quark and its associated antiquark annihilating each other to produce a gluon. Therefore, neutrons and protons don't just each have 3 quarks, since many virtual quarks and antiquarks are constantly being created and annihilated inside both neutrons and protons. But for simplicity, neutrons and protons are typically drawn as just having 3 quarks each. Protons and neutrons have the ability to emit a virtual composite particle consisting of 1 quark and 1 antiquark, which can then be absorbed by another proton or neutron. It's the exchange of these virtual composite particles, consisting of 1 quark and 1 antiquark, that creates the force binding protons to neutrons inside the nucleus of an atom. However, these virtual composite particles consisting of 1 quark and 1 antiquark cannot exist for very long, which is why the force binding protons to neutrons works only over a very short distance. The protons and neutrons in a nucleus therefore have to be very close together for this binding force to work and to overcome the repulsion from the electromagnetic force. The electromagnetic force acts on all objects with an electric charge through the exchange of photons. Photons do not themselves possess an electric charge, and photons will just pass through each other. On the other hand, gluons do possess a color charge, which means that unlike photons, gluons can absorb and emit other gluons, allowing gluons to attract one another. Therefore, whereas the imaginary electric field flux looks like this, if we were to imagine a gluon flux, the gluon flux lines would attract each other to look like this. A consequence of the shapes of these lines is that whereas the electromagnetic force decreases as we increase the distance between charged particles, the strong nuclear force between quarks and antiquarks does not decrease as we increase the distance between them. If we try to separate quarks by applying a large amount of energy, then this energy will be converted into the creation of a new quark and an antiquark. But each quark and each antiquark we create will still be bound to another quark or to another antiquark, and we will not observe individual quarks in isolation. To understand why we don't observe individual quarks in isolation, Hypothetically, suppose we lived in a universe where the electromagnetic force was much, much stronger. In this universe, all electrically charged particles would clump together in a way such that we would get accustomed to the idea that all composite particles must always be electrically neutral. This is the situation we have in our own universe with regards to the strong nuclear force, and we have gotten used to the idea that all composite particles must always be color neutral. A composite particle, such as a proton or neutron, is color neutral if it contains the same amount of red, green, and blue. A composite antimatter particle, such as an antiproton or antineutron, is color neutral if it contains the same amount of anti-red, anti-green, and anti-blue. And a composite particle consisting of one quark and one antiquark is color neutral if it contains the same amount of a color and its associated anticolor. An individual quark can't be color neutral, and therefore we have never seen an individual quark by itself. An individual gluon also can't be color neutral, and an individual gluon also can't exist on its own, as it would never escape the attraction of other gluons. But a combination of two or more gluons could be color neutral, and could therefore exist independently of quarks as what we call a glue ball. Many exotic composite particles consisting of quarks and gluons can be created, provided that they are color neutral, as we do not need to be limited to just the familiar up and down quarks. Though these exotic particles are not very stable,